If you put enough stuff in one place, you'll get a black hole. It doesn't matter if it's steel, carbon nanotubes, or vibranium. According to general relativity, there's no escaping gravitational collapse. Here's why. As you put more and more mass into a given volume of space, the tendency for gravitational collapse increases. After all, the more stuff you have, the stronger each piece of that stuff is being pulled on by all of the other pieces. Now, for a normal piece of matter, like a person or a rock, that gravitational pull is so small that even just single chemical bonds are strong enough to prevent collapse. But for heavier things like stars, you need more than just chemistry. You need heat. For example, if the sun were cold, it just couldn't sustain its large size. It's only because the substances that make up the sun are so hot that it's able to fight off the inevitable gravitational collapse. This works because temperature corresponds to a strong pressure pushing outward. The particles are moving really fast and bumping into each other really hard. This balance, where gravity inward balances thermodynamic pressure outward, is called hydrostatic equilibrium. But this has its limits. It's true that if you put enough material in a small enough region, it'll heat up, but eventually that heat will dissipate and the thermodynamic pressure will fade away, causing contraction. But that doesn't spell the end. For even more dense objects, there's a quantum degeneracy pressure that saves the day. See, one of the rules of quantum mechanics is that no two particles of a certain type called fermions can occupy the same quantum state. And that means that in order to have, say, two electrons in the same place, they would have to have different energy, as an example. And higher energy means that it requires more force to keep it contained. This resistive pressure is called quantum degeneracy pressure, and its presence means that a compact object can resist even stronger gravity without collapsing. As an aside, quantum degeneracy pressure is weird. You can have relativistic speeds for your particles and still have a temperature that's close to absolute zero. But even quantum degeneracy pressure has its limits. For simple systems, we can model how the resistive pressure must increase to withstand the gravitational inward pressure. One simple result, derived by Hans Buchdahl in 1959, implies that the inward gravitational pressure becomes infinite if your gravitational system is a so-called perfect fluid with radius 12.5% bigger than the equivalent black hole radius. As clearly no matter can sustain itself against infinite pressure, such a system can never remain in stable equilibrium once it gets too close to its Schwarzschild radius. Hence, we have an inevitable gravitational collapse. Other, more general results have also been proven. For example, for any material that has a speed of sound that does not exceed the speed of light, the smallest an object can be without gravitationally collapsing is about 8% bigger than its Schwarzschild radius. So unless you think causality can be violated by sound waves, you're out of luck. Now, none of this says anything about what happens at the very center of a black hole, because whatever happens there will be governed by quantum gravity, not general relativity. But what we can say for sure is that above the quantum gravity limit, there is no escape from black hole gravitational collapse.